Hi, my name is Richard Cordero and my topic is driving optimal performance with the ARM and EEL processor. On device, machine learning is a phenomenon that has exploded in popularity. Smart devices that are able to make independent decisions, acting on locally generated data, are hailed as the future of compute for consumer devices. On-device processing/latency, increase reliability and safety, boost privacy and security, all while saving on power and cost. Although NL in edge device has come a long way in a short time, with new networks, new algorithms, and different architectures arriving on the scene in recent years. The basic computational requirements of inference engines has remained constant, since NL is a process of repetition and refinement, aimed at making sense of a vast amount of information and then drawing a conclusion. Functional improvements are still largely driven by high throughput and high efficiency. Pros and cons. Pros. The NL processor optimized design provides a massive uplift in efficiency compared to CPUs and GPUs, and DSPs throughout efficiency, convolution, sparsity, and compression. The NL processor performs convolution with an extremely fast through output of up to 4 tera operations per second, an exceptionally efficient computation rate of 5 TOPS per watt, in a geometry of 7 nanometers. Cons. Common neural network consists of 70 and 90% convolutions. At the heart of these convolutions operations are time-consuming multiple accumulators. The deeper architecture, the more max are required and the longer it takes to process the workload, which, in the case of an edge device, can lead to user frustration. NL is constantly evolving, so it's important to be able to evolve and design to keep it operating optimally. To address this, the Programmable Layer Engine (PLE) enables new operators to be developed in software after the hardware has been designed. These new operators can be included in future firmware updates, enabling future updates after setup or after the device has shipped.
For accelerating machine learning at the edge, which we call the ethos NPs or neural processing units. These range from 1 TOPS in performance to about 4 TOPS at 1 gigahertz worst case. And essentially, they are meant to make your models run much faster at the edge. Compared to a typical Cortex A, depending on which one you're using, we see anywhere from 25 to 30x increase in performance. That's inferences per second. At the same time, achieving a much better power as well as area efficiency. And all of these, they support N8 as well as N16 quantization data types. I'm going to skip this slide. Essentially, what we see at ARM is, while the initial use cases were driven by vision and audio, we see machine learning embedded into every single market. This specifically talks about storage systems where the traditional hash functions are now being replaced by machine learning based techniques, which really help you look up your databases much faster, much more efficiently. And ARM is a lot about partnerships and ecosystems. We are very well known for our ecosystems for Cortex A as well as Cortex M, and we are investing and bringing the same approach to machine learning as well. We are working with a ton of partners for everywhere from generating your models to your middleware to your deployment tools. We are bringing a whole comprehensive ecosystem approach to machine learning because not one company can do everything. There's so many things to do in machine learning that we need the help of a lot more companies to bring the whole solution stack to the market. Um, and essentially, all developers expect open source software or open common interfaces, whether you're working across mobile, IoT infrastructure, or even consumer applications like DTV or set-top boxes, right? And this is a flow, and you probably have seen a variant of this flow in the previous presentations as well, where you have your application running on top, and you connect your inference engine to it, and then you need some sort of a driver or a firmware to help it actually run on the target hardware. Whether the target hardware is your CPU, it could be a GPU in your SoC, or it could even be an ARM NPU. So we have our own inference engine that we call ARM-NN. So ARM-NN sits under your commonly used frameworks, whether it's TensorFlow, TensorFlow Lite, PyTorch, or even Onyx. It's got all the interfaces to talk to these frameworks. It ingests the various graphs from these networks, and then it will optimize those graphs. And then it has various hardware backends plugged into ARM-NN, right? So whether you want to run it on a Cortex-A CPU, whether you want to run it on a Mali GPU or an ARM NPU. ARM-NN can help you do that, right? So essentially, it abstracts away the complexity of hardware from you as a software developer. And just by setting a switch in ARM-NN, you can make the graph run on the CPU or the GPU or the NPU. So the best use case of this is like you basically write an application once, and then depending on what target hardware you're using, you can make it run on any of it. So the benefit is that today you can start developing for something just for a Cortex-A based target hardware, and then tomorrow you have a target hardware platform with a Mali GPU or a, ARM NPU in it. You don't have to rewrite your code. You basically just recompile it using ARM-NN, and the same software code would run on ARM-NN on the target hardware. ARM-NN is open source. It's available under MIT license. So if you have your own custom framework or your own custom hardware, you can take ARM-NN and port it to that as well. It's completely open source. And ARM-NN integrates with various operating systems as well. It's very well integrated with Android NN through the Android NN API. And it works under Linux as well. We support MXNet through Onyx. And as I said, it's open source, so you can even integrate it with your other third-party frameworks and third-party APIs. We work very closely with the Android team to make sure that ARM-NN supports a lot of the operators that Android NN uses. So as far as Android Q, we support almost half the operators that are in Android NN that are required for TensorFlow. And we continue to work with the Android NN team to add more operator support to ARM-NN. So ARM-NN is essentially released on a quarterly cycle. So we continue to add new operators. We add support for new networks that are invented, as well as keep tuning the performance of ARM-NN.
Issue applied in Ecuador. Claro tests 5G in Ecuador. Claro Ecuador has begun testing 5G technology in the city of Guayaquil. The news comes 3 weeks after Daniel Haq, CEO of Claro, parent company American Mobile, announced a $450 million investment in the country over the next 3 years, following a meeting with Ecuador's President Lenin Moreno. Conclusions. Machine learning is quickly growing field in computer science. It has application in nearly every other field of study and is already being implemented commercially because machine learning can solve problems too difficult or time consuming for humans to solve. To describe machine learning in general terms, a variety of models are used to learn patterns in data and make accurate predictions based on the patterns it observes. Thanks for watching the video.